Hello, my name is Lauren Donati. I am a senior undergraduate student studying geology at Indiana University of Pennsylvania. So let's begin my presentation. So today I'll be talking about geology. Geology rocks, the title of my presentation here. Something I want to talk about before we begin is just, so this photo, I was not the one that obviously took it, but the act of geology is just evident in the photo here. Nonetheless, let's just carry on here with the presentation, I guess. Before I begin my talk or my presentation here, I just want to talk about myself a little bit. As I had said, I am studying geology, but while in high school, I never really remembered learning about geology, only small pieces of information, like what quartz and muscovite look like, or that trilobites are our state fossil. Apparently this was enough information for me to become interested in geology, but I understand that that is not enough information for everyone. So I'm going to talk a little bit about the field of geology and a lot about what I am currently doing in geology during my undergraduate years. All right, moving on. So what is geology? Geology is the science that deals with the Earth's physical structures and substances, its history, and the processes that act on it. So geology in some way or another affects everyone. So from the lithium in the batteries of cell phones to the copper wires in homes to flat out regions that are threatened by landslides, volcanoes, earthquakes, or floods. Geologic hazards like that affect a lot of places all over the United States and all over the world. It's really important for people living in those regions to be aware of those types of geological hazards. So moving on, the images in this slide are typically associated and or used to describe geology in general. The large time scale that I have to the left here just simply tells the story of Earth. Obviously, it's an old one. Some information, I guess, about the time scale that I just wanted to mention that I found personally interesting is, so here in the Devonian, it's known as the age of the fish, but during the Devonian, trees were also forming on small portions of land that were obviously not underwater. And because the niche space was not filled by anything, because it was the age of the fish, these trees eventually died and formed the Marcellus Shale geologic unit, which again is obviously just interesting. And then you can also see in the Cambrian or near the Cambrian era here, we have some trilobites forming, which again is our state fossil. Nonetheless, so these other images that I have here, we have the mantle, the outer core, and the inner core, or what's just inside the Earth, right? So again, these are just hypothesized. We are not able to get any samples or go into the mantle, the outer core, or the inner core. But we do have volcanoes where we get chemical makeup of the mantle, and we're able to test that kind of data. S waves are able to transmit through the Earth, and once they hit the outer core, we see that they don't really transmit through it, meaning that it's most likely liquid. Again, we're just using this type of evidence to support the hypotheses of what's in the Earth, right? So moving on, the image below is something we as normal people see on an everyday basis and how we sort of interact and see geology. So this image was actually taken by myself on a class field trip to the Pennsylvania Turnpike. So the Pennsylvania Turnpike is actually pretty cool. We see a lot of geology on it. Outcrops are beautifully presented and preserved on the Turnpike. here we see an anticline, which just means that the limbs of the geologic unit here are folded downward. And then we can see different evidences of geology, slope failure, slope movement, stuff like that. So moving on, I just want to expand further very shortly about the different branches of geoscience. So starting forward, obviously I don't have images here of every single branch, but I'll sort of talk about each one a little bit. So first off, we have mineralogy and petrography. I am able to use a little bit of petrography. Again, this is just identification of minerals, looking at them through microscopes, just identifying structures within thin sections typically. Then we have structural geology / tectonics. You can see a little bit of a picture here about structural geology right here. See those folds. Again, structural geology is just the different structures that we see. It does deal a lot with like plate tectonics and that type of geology. Moving on, we do have stratigraphy, which is just how the geologic units sort of lie. A great example of this is what we see in these cores. I think from around Antarctica, a couple of our professors have been down there quite often and bring back a lot of cores. So these different units can indicate different things that were going on in that environment through the geologic timescale, which is actually very interesting. And when you actually look at the samples, it's not just all gray or different shades of gray. You can see a lot of information within. Moving on, we have paleontology, which is always a fun one. Everyone sort of knows about paleontology in the fossil record. And then there's just image right there that I have of a dinosaur fossil. Moving on, we have one of my favorite branches is hydrology and coastal geology. I do have an image here of my class on the Delaware coastline. We're just working on the beach face here, taking information about low tide, high tide, and the swash zone. It's just interesting type of study that I find most interesting. Moving on, we have geophysics, which is pretty simple. It's just physics mixed in with geology. In the image here to the left, I talk a little bit, or I have an image of ground penetrating radar, or GPR. It just takes some information and we can see into the earth from a small depth, but it's very interesting and pretty helpful. Moving on, we have geochemistry, which is obviously pretty self-explanatory, just chemistry with geology. And then finally, we do have geodezy, which is just understanding the Earth's geometric shape from a larger scale. And now there are a couple other branches, but they do sort of combine the ones I've already talked about. Many of these branches are combinable in to advanced research. I do use I do use mineralogy to help advance my research in structural geology on a micro scale. Who knew? Geology is just a little bit more than just rocks. So let's continue. So moving on, I'm going to expand on my work specifically. My research group aims to document the plastic to brittle transition to provide constraints on the rapid exhumation of the eastern foothills of Taiwan, thus to improve modeling efforts of the tectonically active island. So what does this mean? So plastic structures and brittle structures. So the rocks in Taiwan are metamorphic, meaning that they at one point had a lot of heat and pressure interacting with them. So when a lot of heat and pressure are added, rocks behave plastically and are able to flow and bend and fold. So that kind of behavior can be preserved in the rock as it is exhumed and brought closer to the surface because the rock begins to solidify. And that's when brittle deformation occurs to these rocks, which is just fracturing in them as it moves closer to the surface. So that type of thing would be joints when they fracture. And I'll talk a little bit more about that as we keep going here. So we are stating that Taiwan has a complicated deformation history and formation in general. And we are focusing on constraining the plastic to brittle deformation, which can be extracted from the plastic to brittle structures along river outcrops. My work specifically focuses heavily on the transition from that early plastic behavior of the structures to the early brittle deformation that happens within these structures. So twice I was able to travel to Taiwan on the eastern foothills for 3 weeks periods, investigating structural geology of 100-kilometer field area or 62 miles of study area, recording the attributes of the structures like faults, which is just fractures in rocks on a larger scale, joints, veins, and collecting rock samples. So again, joints are just natural breaks in the rock. Veins are bodies of crystallized minerals that fill these types of joints, or these breaks in the rocks. And the faults and joints would be considered brittle behavior, while the veins could be considered a transition period between the plastic and the brittle deformation history, obviously. So then moving on, we're able to create a master file of this kind of data and interpret it how we need to in our research. The presentations here to the left. So in my opinion, my research wasn't perfect in the beginning. My first poster over here, I focused on individual hand sample collected from the Mugwa River. While the analysis wasn't perfect, we were able to identify the sample as rather important to Taiwan's history. The poster presentation to the right, however, has an improved examination on the brittle deformation, where we identified patterns of extension to the northeast southwest. As you can see in the poster here, we sort of had the arrows pointed towards the northeast southwest for not only joints and faults, but also earthquakes. So we're identifying a pattern between the brittle structures, which is rather important to identify these types of patterns for modeling efforts, as that's our main goal to help improve the constraints on modeling efforts. Again, it's important to get these types of research on a larger scale. So that would be our end goal, is to get more data and collect it from the field to get a larger presentation on this type of data. So in this slide, I'm sort of talking about our new data that we presented this year and the patterns that we're trying to identify. So it's all similar data that we're working with, just trying to identify new patterns or enhance the data set. Okay, so in this poster to the left, this would be mine. I'm identifying plastic to brittle structures, as you can see in that small little box right there. I also identify a northeast southwest extension and vertical shortening in the plastic structure and the brittle structures, which is similar to what we saw before. While in the plastic structures, I've identified a gentle dipping, mostly north orientation, which is good just for recording these types of patterns. While we might not know what it means right now, we are able to use it later on for determining what we're seeing in modeling efforts. In this poster, we have improved our strain analysis and petrographic analysis of the sample that I was speaking of earlier. Within this improved process, we have found evidence for a weak overprinting stretching lineation. So the fabric indicates stretching in a certain direction. In particular, this sample has found a strong stretching lineation or a strong pattern in one direction and then a weaker one in another. The reason why this is rather important is because in this area, we typically don't see both stretching lineations or two stretching lineations preserved in this type of sample. We either see one or another. So what this sort of indicates to us is that, or from previous work, we found that one type of stretching lineation is found on the west side of the island, while a different stretching lineation, very similarly, is found on the right side. So what this could indicate to us is that the transition is found within this rock, which makes it rather important for future research in what we want to find on a larger scale. Because if we find similar samples, this could identify the boundary on a large scale, and we could mark it on or identify it on the island. Which is thus important to find more modeling efforts. As I explained, that's our overarching goal, to improve modeling of this island and understand its formation. So the poster to the right uses an enhanced data set and elements from the other poster that we spoke of before to improve or confirm what we found before. So this enhanced data set does confirm that we see a northeast-southwest extension to the northeast-southwest. Similar to my poster, I did find the similar type of data, but this one to the right does use earthquake data. So again, confirming that these brittle structures in a larger data set do still see northeast-southwest extension on the brittle structures. So that's an overall overview of our super exciting and sometimes rather boring tectonic research that we are doing at IUP. Moving on. So my current research, we are always trying to continue our research. We are NSF funded, or we are funded by the National Science Foundation. So we would like to present our data and find information, present it, and contribute to the science community. However, COVID has made that rather hard, for me at least. A lot of my data a lot of my research tools are at school. So I have found a way around that to keep continuing my research. I'm using the same sample that I've been using for a while now, since that first poster that I talked about. And I have a lot of thin sections of this, so I'm going to sort of talk about what I'm doing with it. So there's a lot to unpack within this thin section, or within this sample in general, meaning that it could be worked on for many years after I graduate, and more publishable data could be found about this sample and others near it or contribute to it. So I will soon be working on mapping deformation mechanism types seen in microstructures within several thin sections. Here I've included two of the example images of the thin sections I'll be using to look for microstructures. It's a little hard to see, I believe, at first, and a little hard to explain, so I'll try to break it down a little bit. So in the image to the left here, we see thin sections presented in plain light. So just a plain light is shining through the thin section, so we can see the different structures and lineations within. So as you can see, there's a lot of black lines. This is pressure shadow solution. It's just rocks that were not able to be dissolved all the way, and so you can see it, a thin line of them clumped together right there. And this sort of indicates, it's a good indicator of the different deformation mechanisms that we see within this section. So I can highlight a few out here that we've talked about before I started my research. So, sorry, I don't know if you can see it here. So this little black line right here caps a lot of the structures within this thin section. You can see something over here and something right here that stretches rather far. But what's important is if you look to the right, you'll also see the same image, but in cross-polarized light. So it basically has a filter over it to show me or let us be able to see the color within these clasts. So what's important about this right image is that in these images where I've already identified the pressure shadow solution, or these black lines, like I was saying, it can show us what's been recrystallized and how it's been recrystallized. So it can either be done statically or dynamically. So typically what we'd see if it was done statically is that the grains and the boundaries of these grains would be less complex than they were before recrystallization. So you can see it. Yep, perfect. So as you can see, the boundaries of this sample are rather simple. They're pretty straight ahead, right? So we consider that pretty static deformation. So again, static, not moving, right? While in the same sample, we see more of a dynamic recrystallization. So this is a great example of that right here. The boundary looks like it sort of locks up just like this, which is rather interesting. And we consider that dynamic, and that's something I would map in my analysis later on. So currently, the analysis is ongoing, and we hope to have some data that's publishable in our paper for expected 2021. While this research isn't currently super exciting, I hope it's encouraging you to look into geology and the many other branches of it. It's not just rocks. It can be super interesting. While this might not seem it, it can be. Moving on from here, I'm sorry I wasn't able to be here in person with a live Zoom, but I hope in the coming years I'd be able to come back and talk a little bit more about a different branch of geology that I'm in, or I hope to be in during grad school, in hydrology and coastal geology, looking at climate change and how that's going to be affecting us in the coming years. I've attached my school email here for those that might have some questions about IUP and geology in general. If you do have any questions, please don't hesitate to ask. Thank you. Thank you for your time, guys. Have a good day.